Hi viewers. Welcome to this presentation on flexible AC transmission system. Transmission lines have four electrical parameters. Capacitance C is due to pair of conductors having air as dielectric between. Inductance L is due to flow of current through conductor producing altering magnetic field around. Resistance R is obstruction to flow of current due to atomic structure of conductor material. Leakage conductance G account for leakage current between conductor and or ground through air and or insulators. Capacitance C of line depends on following. Spacing between conductors. Conductor diameter. Dielectric constant of insulation. Height of conductors above ground. Length of the line. Inductance L of line depends on following. Spacing between conductors. Conductor diameter. Permeability of surrounding material. Length of the line. Resistance R of line depends on following. Resistivity or specific resistance of the material of conductor used in line. Length of the line. Cross-section or area for current flow through line. Leakage conductance G of line depends on following. Insulation material. Weather conditions. Insulator design. Line voltage. Line length. Number of insulators or line supports. Occasionally line constants A, B, C and D are derived from above C, L, R and G to analyze line performance in complex network. A is equal to voltage ratio, receive by send. B is equal to transfer impedance. C is equal to transfer admittance. D is equal to current ratio, receive by send. Once any line is designed, installed and commissioned, these parameters are fixed and do not change. However, it is observed that line behaves as capacitive or inductive element of power system at different times. This appears to be erratic, yet it is the observed fact. This phenomena concern with capacitance C and inductance L of line. Resistance R and conductance G of line has no influence in the matter. Therefore, role of capacitance and inductance of line is analyzed. This is ideal model of line. Capacitance is between the conductors distributed throughout the line. Inductance is along the conductor distributed throughout the line. The figure represents only one pair of conductors for clarity. Actually, each of the three conductors have inductance and each of three pairs of conductors has capacitance. The basic model is simplified with total lumped capacitance C and total lumped inductance L. T-equivalent circuit. Lumped capacitance C is considered between two halves of lumped inductance L as in the figure. Pi equivalent circuit. Lumped inductance L is considered between two halves of lumped capacitance C as in the figure. Line capacitance is between the conductors as in equivalent circuit. So it gets energized when supply fed from any end and draw charging current. Line capacitance is equal to C. Capacitive reactance XC is equal to 1 divided by 2 pi FC. Charging current is equal to V divided by XC. Reactive power is equal to V square divided by XC. This is capacitive reactive power, is dependent on supply voltage only and is independent of load on the line. Switching on line from any one end is therefore called line charging. There is no power flow through line till the other end is open. Open end voltage may be higher than charging end voltage. This phenomenon is known as Ferranti effect. Therefore, line reactor is connected at other end before charging the line to avoid high voltage at open end. This is chart of reactive power versus loading on line. Inductive reactive power is considered positive as per general conventional. Therefore, capacitive reactive power can be negative because of opposite to inductive power. Hence, green curve of capacitive power appears below the x-axis on chart. Line inductance is along the conductor. Load current flows through inductance of the line. Line inductance is equal to L. Inductive reactance XL is equal to 2 pi FL. Reactive power is equal to I square XL. This means inductive reactive power of the line is proportional to square of load current. This red curve of inductive power appears above x-axis as per convention. Inductive and capacitive powers are opposite and hence cancel each other. Net reactive power of the line at various load is sum, algebraic, of these two as orange curve in the chart. This orange curve of net reactive power crosses x-axis at SIL. Inductive reactive power and capacitive reactive power are equals at this load. So net reactive power is 0. Line load at which this occurs is surge impedance loading, in short SIL of the line. Net reactive power of line is nil at SIL. Line do not deliver nor absorb reactive power to from the system. Line behave like capacitive element and inject reactive power in the system when load on line is less than SIL. Magnitude of reactive power injected depends on deviation of line load from SIL. Capacitive power is maximum on no load when line is charged from one end only. Similarly, line behave like inductive element and absorb reactive power from the system when load on line is more than SIL. Magnitude of reactive power absorbed from the system depends on line load above SIL. Therefore, ideal operating conditions for line is to have load at or close to SIL. But load on the lines depends on locations of power sources, locations of load centers and parallel paths in system network. So it is impractical to operate all the lines all the times at load close to SIL. However, there is alternate way to achieve the target. Modifying SIL level of the line to match load on line. SIL level depends on capacitance and inductance of the line. These can be modified by adding external capacitor and or inductor as required. Adding capacitance C means decrease capacitive reactance XC and ultimately increasing reactive power V square divided XC. It is evident from the chart that increase in capacitive power will shift SIL toward higher load. Adding inductance L means increase inductive reactance XL and ultimately increasing reactive power I square XL. It is evident from the chart that increase in inductive power will shift SIL toward lower load. Capacitive or inductive elements can be connected in series or shunt to line. Elements added in series with line are subjected to load current of the line including overload and short time fault current. Therefore, current rating required accordingly. But voltage across the added element is very small, equal to drop due to load current. Elements added across the line, shunt or parallel, with line are subjected to system line voltages and surges. Insulation system needs accordingly. But current rating required is limited to its V upon X only. It is not subjected to load current. The reactive power of the series element varies with the load. Capacitor added in line seems to have self-regulating feature because capacitive power of added element vary with inductive power of line at various load conditions. But it can be connected other way also as suitable. Reactive power of shunt element remains fixed. Inductor added as shunt element may compensate fixed capacitive power of the line. But it can be connected other way also as suitable. Such corrective element to attach to line may be capacitive or inductive or combined. These may be automatic adjustable to match the real-time requirement. Devices have advanced control system through thyristor or IGBT along with monitoring sensors and programmed with appropriate algorithm. Corrective elements associated with transmission line makes it flexible for ideal operating condition at different loading. Therefore, it is referred to as flexible alternating current transmission system, FACTS. Corrective elements used for the purpose are FACTS devices. Various FACTS devices. Thyristor-controlled series capacitors, TCSC. Static synchronous series compensators, SSSC. Static var compensator, SVC. Static synchronous compensator, STATCOM. Unified power flow controller, UPFC. Distributed power flow controller, DPFC. Thyristor-controlled phase shifting transformer, TCPST. Thyristor-switched capacitor, TSC. Thyristor-controlled reactor, TCR. These FACTS devices also helps improve the efficiency and reliability in addition to flexibility of power transmission. It may enhance power transfer capability, increase stability, controllability, congestion management, loss optimization, damping to inter-area oscillations, fast reactive power control, etc. Transmission system expert selects appropriate device from above according to scope for particular link. Please like, subscribe and recommend others if found worthy. Viewers' comments welcome. Thank you viewers. Bye until meet again in next episode.